Yeah, so last time we discussed about Hermitian operator and unitary operator on a Hermitian. So we defined Hermitian space and we talked about Hermitian operator and unitary operator. Basically, we defined also adjoint operator, and we saw that Hermitian operator, it is a Hermitian operator if and only if its adjoint is itself. So Hermitian operator have another name. It's called self-adjoint. Yeah, more enlightening one is the self-adjoint operator. It's also called self-adjoint. Okay, so okay, I don't know. Today I used to be able to see your so I don't know why. As soon as I click on this, it goes away. Huh. So so we saw last time that when t is t is Hermitian if and only if we have the linear operator t is Hermitian if and only if tv comma w is same as v comma tw for all v and w in v, right? And we also saw that unitary means this, meaning so I sort of stated it, and we saw the proof in the forward direction is so the proof is straightforward. So for one, this is the forward direction is tautology, because we know. So recall last time we saw that in general, by the definition of T star, we know that by definition of T star, we have mod TVW is same as V T star W, right? This was basically, this you can sort of say is small as the definition of T star. Yeah, so so we'll see how so meaning T star was defined as you take the matrix of T with respect to some orthonormal basis and take the adjoint of that matrix and use that to define T star. Right. So so let's see the backward implication. So for instance, we want to show that T star if this TVW is equal to VTW, then T star is T. Yeah. So then we want to say that T star is same as T. So what you do is look at V comma T star minus TW. Yeah. So we want to show that T star minus T is 0. So let's see what it does to a vector W. Yeah. So by, T is a linear map. So or anyway, T star minus TW means T star W minus TW. Yeah, that is how the linear operator is defined. And so remember, T star minus T is again a linear operator, and we want to show that this linear operator is 0. So what you do is you look at this. So it's additive in the second. It's actually linear in the second coordinate. Additive is good enough for us in this case. And this becomes V comma T star W minus V comma TW. But remember, by our hypothesis now, T star is same as T. So this is this. So maybe either, am I trying to, no, I want to prove T star is T. Yeah. So what happens is now V comma T star W is same as TV comma W by this by what we had seen last time. Yeah. V comma W is same as V comma T star W. So we get this. And the second one is by the hypothesis. The hypothesis says that TVW is VTW. Yeah. So both are same. So what we get is this is 0, and this is true for all VW. Yeah. So every VW in uh, in the vector space V, this identity holds that this difference is 0. So that tells you that T star must be equal to T. Yeah? For instance, you can take I guess you can take V to be T star minus TW. Then we know that this inner, since this is a what? This is a same positive definite Hermitian form. Then this pairing has to be strictly positive if you take V to be this guy, because it's taking the inner product of the same guy with itself. It should be strictly positive if it is non-zero. So from there you can conclude T star minus TW is 0. And this is for all W in W. Yeah, hence T star is. So that proves the backward implication for 1. Is this okay? Yeah. So, and the same thing for unitary. So you want to show that T star minus T star times T is identity. If So this first if and only if is by definition, yeah, is the second if and only if which we are trying to prove. Yeah. So we are trying to prove these guys. Yeah. So the first if and only if is by definition. Yeah. But the second one is what we are trying to prove. Okay. So for the so we will assume TW is VW, the pairing between V and VW, and we want to show T star T is identity. So again, what you do is take T star T, subtract identity, and want to show that it's a zero map. So we will do that. So note VW is same as TW by hypothesis. The first equality is hypothesis. Second equality is you are moving T to the other side. So it becomes T star. Yeah. So this equality tells you, so if you take the difference, then it's linear in the second variable, so it becomes V comma identity minus T star TW. Yeah, so it's W minus T star TW, but W I can write it as identity of W, so it becomes this linear operator W equals 0. And this is again true for all V and W. So again, that tells you that identity minus T star T W is 0. For all W in W, that is same as saying T star T is identity. Okay. Yeah, so this is the usual. So non-degeneracy gives you, so as soon as you have V comma TW is 0 for all V and W, that non-degeneracy tells you that T must be the 0 map. Okay. So that is you don't even need positive definite, just non-degeneracy is enough. Yeah. So that is what we are using. And then, so I had stated the spectral theorem for self-adjoint operator. So today we'll see a proof of it. So there is some question, yeah. T is a rigid motion. Yeah, but this is but this is not some. So it is not a priori. You'll have to then argue that it is the distance map. Yeah. So we are not working over Cn or something. Yeah, we are working over some particular or some arbitrary vector space, and this pairing need not be the distance. So one can argue that way, but then you'll have to show that this is also same as the distance, and then argue it that way. Yeah, so one can do it that way as well, but then you'll have to say that this is same as the distance. Yeah, and then this pairing defines the distance. And then, of course, you can argue that this is distance preserving or not, and hence it's a unitary operator. Okay. Okay, so let's see the let's see the spectral theorem. So let T be a Hermitian self-adjoint operator on a Hermitian space, Hermitian or self-adjoint, whatever you like, they're the same thing. Then there is an orthonormal basis of V consisting of eigenvectors of P. Yeah, so this is the spectral theorem, and it has some translation in terms of matrices, which I mentioned last time. So maybe after the proof of spectral theorem, we'll mention that. Yeah. So let's see a proof. So here, this is where sort of if we think somewhat abstractly, things become somewhat, instead of working with matrices, working with vector space becomes somewhat easy. So we want to get an orthonormal basis. So of course, this is straightforward if dimension of V is 1. So we'll use induction on dimension. Yeah. So if dimension V equals 1, nothing to prove. Yeah, because I mean it's a positive definite pairing. So you take any vector and the length of the vector is going to be positive. Any non-zero vector in V, length is going to be positive. You scale it, so you'll get a orthonormal vector, unit vector, and it of course spans V. So that is that is, I mean, for one dimensional, everything is an eigenvector. Yeah, every non-zero vector is an eigenvector. So now so what you do is T is an operator on a complex vector space. So of course it has eigenvalues and eigenvectors. Yeah. So let V be an eigenvector of T. First, so do I need to look at the eigen? Yeah, so maybe I don't care about what the eigenvalue is. But maybe if I think, V be an eigenvector of T with eigenvalue lambda, let's say. Yeah. So what you do, you look at, let's call it V1. So this will be the start of orthonormal basis. Yeah, so V1 is and let W be the set of vectors V in V such that V comma V1 is 0. Yeah. So in other words, W is the orthogonal complement. Yeah. So of course, this is a non-degenerate, it's a positive definite pairing, non-degenerate pairing in particular. So you can write W as direct sum of these two. Yeah. So one can write, so hence V is W direct sum. Okay. So dimension of V pulp is the W direct sum V. Yeah. So V pulp is W, so we can't get W direct sum V pulp. W direct sum V. Yeah. So, and remember, and dimension of W is dimension of V minus 1. Yeah. So we know the we know the result for W as long as we can say that W is a, so of course the note. Yeah, so we'll have to show that W satisfies all our hypotheses. So there is another. Yeah, V1. That's right. You can speak. Yeah, interrupt me if when I'm sort of making some.
Sir, am I audible, sir?
Yeah, you're audible. So you can tell. You can speak.
Actually, I called you last time, but I think you couldn't hear.
I see. I see. Yeah, then maybe you call my phone if I don't hear. Yeah. But we can yeah, we can talk. It's much more
Yes.
easier, so, or rather livelier if we can hear each other. Yeah. So yeah. So this is V is W dx some V1, and this is what. So what the claim is T restricted. So first of all, W, of course, W. This is I mean this is obvious. W with this pairing, yeah, which V is a Hermitian space, yeah. So you can restrict this to W is a Hermitian space. So this is not at all. I mean, this is obvious, but and T T T of W is contained in W. Yeah. So T restricted to W is an endomorphism. Yeah, so it will be a Hermitian operator. So T is again, so T is a Hermitian operator on V, and if T sends W to W, then it is a Hermitian operator on W, and then we can use induction hypothesis to get the orthonormal basis for W. Yeah. So once we have this claim, the rest is easy. So proof. So of course. This restricted to W is positive definite. I mean it is a positive definite Hermitian form. Hermitian form. So maybe this restricted to W, I should say, as this is positive definite Hermitian form. Yeah. So to check it is a Hermitian form is you check it element wise. So if it is true for all elements of V, now of course it is true for all elements of W because W is a subspace. Yeah. And positive definite also you can check element wise. Yeah. Elements of the vector. So for all V in V, the inner product of V with itself, the pairing of V with itself is should be positive if V is non-zero. So same holds for W as well. Yeah, so this is okay. So now let's just check TW is contained in W. Yeah. So well, TW. So to check that TW is so let W be in W. So this implies that the inner product of W with V1 is 0. Yeah. And to show that TW belongs to W, we'll have to check that TW inner product V1 is also 0. Yeah. So let's see what happens to TW. So TW inner product V1. Yeah. So why is it 0?
W star V1 and T
Yeah, so
star.
we can move it the other side. Yeah, so it's a self-adjoint operator. So this is ideally we should put T star, but self-adjoint tells you we can put this. Yeah. And TV1, what is TV1?
eigenvectors, so you will have a lambda.
Yeah, so it's some scalar times v1, yeah, which we have called it something lambda, yeah. So this is w comma lambda v1, and lambda also we can pull out lambda w v1. It's linear in the second variable, so even if it was conjugate linear, you could have pulled out lambda bar. It doesn't matter. But anyway, so this is 0. Yeah, so this tells us that TW is in W. Yeah, so TW is orthogonal to V1, so it has to be in W. So this proves the claim. Yeah, that TW is contained in W. So T restricted to W is a Hermitian operator on the Hermitian space V, this thing. Hence, by induction hypothesis, there exists V2 to Vn and minus 1 orthonormal basis of W. So they are orthogonal to each other and all their lengths are 1. And then of course the set V1 to Vn is orthonormal. I mean V1 is orthogonal to everything. Yeah. So it is orthogonal to V2 to Vn and it has norm 1. So did I choose that? So let V1 be an eigenvector of T of norm 1 such that. So maybe I should have taken that. Yeah. That. So this we can ensure. Yeah. Whatever the norm is, you just divide by the length of it. So is orthonormal basis of T. Okay, any questions or comments?
So don't we need to prove that V2, etc., Vn are eigenvectors?
Sorry. So this is orthonormal basis consisting of eigenvectors of T. That is how I orthonormal. So induction hypothesis. Yeah, not just some. Sorry. Yeah, good point. So orthonormal basis of W, where with V2 to Vn, eigenvectors. Yeah, sorry. So maybe I'll just write it more here. There's this orthonormal with. I mean, we didn't apply the induction hypothesis correctly. Yeah, V2 to Vn completely as eigenvectors. So T restricted to W. So that means T V2 is some lambda 2 times V2 and so on. Yeah, so they are eigenvectors. So if they are eigenvectors of W, then T restricted, then they are eigenvectors of T as well, right? Yeah. V1 to Vn are eigenvectors of T and an orthonormal basis Okay, is that fine?
Yes.
So that is the thing we wanted to prove, that there is an orthonormal basis of V consisting of eigenvectors of T. Okay, so this is done. Yeah, so now any questions or comments?
Are you speaking because we cannot hear you?
I have been speaking. Since when did you not hear me?
Since after the proofs.
After the okay. Yeah, I've been telling. So I don't know, somehow it got muted. So let A be a Hermitian matrix, then there exists a unitary matrix P such that P inverse AP is same as P star AP. Because P inverse P, remember, unitary means that P star P is identity. Yeah, so inverse is same as this, is diagonal. Yeah, so I mean I can write. So basically, what it says is every Hermitian matrix is diagonalizable, and is diagonalizable by, in fact, a unitary matrix. Yeah, that is what a consequence of this thing is. So if you want to write that in terms of matrices, this is what it is. Yeah, so let's see. So let's see how you'll prove this using the previous using the spectral theorem. So you take Cn to be your vector space. So if A is n cross n, A is n cross n, then Cn is the vector space with and you take the standard Hermitian form. Yeah. So Cn with standard Hermitian form is our Hermitian space. Then A multiplication by A defines a Hermitian operator on Cn with standard Hermitian form. Yeah, so I don't know. Should I give? Let's call it standard Hermitian form. On this thing, yeah. So by this spectral theorem, there exists there is an orthonormal basis of V consisting of eigenvectors of T. Yeah. So so by spectral theorem, there exist vectors. Let's call it column vectors V1 to Vn in Cn. Eigenvectors of A and V1 to Vn are orthonormal vectors. Orthonormal with respect to standard, with respect to this standard Hermitian form. Yeah. So what does it mean? So if V1 is I don't know, A1 to let's not call it A. V1 is, let's say, X1 to Xn, and V2 is Y1 to Yn, Y1 to Yn. Then what it means is that summation Xi bar Yi is 0, I equals 1 to n. Yeah. And summation Xi bar Xi, I equals 1 to n is 1. Yeah. And similarly, summation. So this is what these are some consequences of what orthonormal vectors mean. Yeah. So we have this. So what is our P? So you can take P to be this matrix V1. So the columns of P are V1, V2, and so on, Vn. Yeah. So you consider this is a n cross n matrix. Yeah. And what is P star? P star is V1 star is going to be this thing, yeah, Vn star. So V1 star becomes a so V1 is a column vector, right? So V1 star becomes a row vector. So we'll have to stack the rows to get a n cross n matrix. Is this okay? Yeah. And then so what is P star? P star P. So if you think about it, P star P, so the diagonal entries are going to be, so entries are going to be V1 star, Vi star, Vj star. Yeah, so it's going to be so ijth entry is going to be Vi star, Vj star. So it is, so maybe I'll write it in okay, somehow it is stuck. Hello, can you hear me?
Yes, sir.
Okay, so the problem is probably with the, but my computer is hung, so I don't know what is the problem. Nothing is working. Okay, yeah, so something started working. Let's see. Yeah. Okay. Yeah, so this we can write it as Vi star Vj. Yeah. So the ijth entry is Vi star Vj if you take this product. But this, by our definition that this is an orthonormal basis tells you that this is identity. Yeah. So Vi star Vj is 0 if I is different from J, and if I equals J, then it is 1. Yeah. So P star P is identity, and moreover, it consists of orthonormal bases. So it consists of eigenvectors. So P star AP, if you so P is going to be yeah. So AP is basically yeah. So A times P is so since these are eigenvectors with eigenvalues, let's say lambda1 to lambda n, then A times P is just A times V1 is lambda1 times V1. A times P V2 is lambda2 times V2 and so on. Yeah. Lambda n times Vn. And if you now multiply P star with this, then you of course get so P star is this thing, yeah. So I mean you'll get so this is maybe, so let me write in the same notation. So this will be lambda j times Vi star Vj, yeah. So of course, if I is different from j, then this is again 0 and 0, and if I is equal to j, then it is lambda j. So it becomes lambda 1 to lambda. Diagonal. Is this okay?
Yes, yes.
Yeah. So this proves the matrix form as well of the spectral theorem. Okay. So is there anything else I wanted to say before starting normal operators? Yeah, so another corollary is, so this is about complex ones, but you can do make some statement about real matrices as well. So corollary. Yeah. Something went wrong. Yeah. So corollary. Let A be a real symmetric matrix. Then yeah, so then again A is diagonalizable. There exists yeah, so then there exists and so this maybe I'll leave it as a homework. Orthogonal matrix P. So now not unitary, but orthogonal matrix P such that P transpose AP, which is orthogonal means P transpose P is identity, yeah. P inverse AP is diagonal. Okay. So so there exists a unitary matrix. So of course, the fact that there exists a unitary matrix with this property is obvious. Yeah, it follows because a real symmetric matrix is automatically Hermitian. Yeah, because conjugate doesn't do anything. So the content of this is that you can actually find not just unitary but orthogonal. So orthogonal matrix. Yeah, so maybe you can argue this yourself, why you can find orthogonal matrix. Is that okay? So maybe I'll leave it as a homework. Why you can do this. Okay. Yeah, so now maybe some examples before we get to normal. Before we get to normal operators. Maybe it's not visible. Let me restart this OneNote. Yeah, it's acting up. So yeah, so you can see the screen. Yeah.
Yes, sir.
Okay. So let's work out some examples and see what happens. Yeah. So for instance, let's look at this matrix A. Yeah. So I mean, it's so for 2 by 2 anyway, it's sort of easy to figure out things, but I mean, here you don't even have to do any computation. Yeah, you just look at the matrix and you realize that it's Hermitian. Yeah, self-adjoint. So it has to be diagonalizable. Of course, if you want to write down the exact so to say whether it's diagonalizable or not is straightforward by just looking at the structure of the matrix. But to find out which a unitary operator is going to do it is going to be a little bit of work. Yeah, so you'll have to find the eigenvectors. In fact, you as soon as you find the eigenvectors, then also you are more or less done. Yeah. So I'll tell you how you are more or less done if it is so. For instance, in this one, you look at the characteristic polynomial of this thing. So you get that is t minus 1 whole square plus 4 times I square. Yeah. So you get 4 times minus 1, and you get that the eigenvalues are 3 and minus 1. Yeah. So I have just done this calculation, and it comes out to be 3 and minus 1. Okay. Yeah. Nonsense. What is wrong with this? Okay. Yeah, so you get that the eigenvalues are 3 and minus 1. And then once you know the eigenvalue, it's easier to figure out the eigenvector. Yeah. So if eigenvalue is 3, how do you figure out the eigenvector? You try to find what is in the kernel of a minus 3i. Yeah. So you calculate a minus 3i. So that is what I'm doing here. So it's minus 2, 2i minus 2i minus 2. Yeah. So we know that it has to be rank 1. So if you think about it, if why is this rank 1? Why is the first row a multiple of the second row? So the point is, if you multiply by I, the first row, then you get the second row. Yeah. Because it becomes 2i, and this 2i becomes 2i square, which is minus 2. Yeah. So if you multiply the first row by I, then you get the second row. So if you take I, so if you multiply this matrix by I times minus 1, you'll get 0. Yeah. So that tells you that this is an eigenvector. Yeah. And similarly, for for eigenvector for eigenvalue 3, and similarly for -1, you look at a plus I, and so maybe I can make this a little smaller. Yeah, so you look at a plus I, and then the eigenvector. So if you multiply by I, you don't get the bottom row, you get the negative of the bottom row. So the eigenvector is I comma 1. Yeah, so I1. So these are the eigenvectors. And of course, the eigenvectors have to be orthogonal, right? Because, I mean, that's what the theorem says. So they are distinct eigenvectors. So the eigenvalues are distinct. So there's, I mean, the eigenspace corresponding to 3, there is only one eigenvector. It's not like that, more than one. So every eigenvector for 3 is going to be a scalar multiple of it. So this has to, and you can of course check as well. So you can check I minus 1 and 1 I1. So this is orthogonal, right? So you get I minus I squared plus 1. So minus 1. Minus 1 times 1 is, so minus I squared minus 1, and minus I squared is plus 1. So plus 1 minus 1 is 0. Yeah. So is it okay? So this is these are orthogonal, but you'll have to make it orthonormal. You'll have to do something. Yeah. So I guess I don't know. So the P in this case, so I don't have space here, so maybe I'll write somewhere. Yeah, maybe P in this case is going to be yeah. So but the norm is not 1. What is the norm of this thing? What is the inner product of this with itself? Am I out? Yeah, I'm audible. Yeah. So what is the inner product with itself? Say it louder.
0.
It can't be 0, no? It's, how can it be 0? So what is the what is this? You are trying to compute this, right? It has to be positive number. Yeah, that we know. So how do you? I mean, to compute the inner product, what do you do? So you will have to take. So what is the formula? It's written here somewhere. Yeah. xi bar yi. Yeah. Summation xi bar yi is the formula. Yeah. So the inner product is so x1 bar is minus I, and y1 is I. So it becomes -1 minus I squared plus this bar is 1 itself, and this bar is 1. So this, yeah. So maybe let's forget about this sum thing. So what you get is this is 0. This is not 0. Yeah, this is 2. Minus I square is not, I square is -1, minus I square is 1. Yeah, so this is 2. Right?
Yes.
So this is 2. So the norm is going to be 1 over, it will be square root 2. So if we divide by square root 2, and the norm of I1 is also square root 2. Yeah. So if I divide by square root 2, then it becomes an orthonormal, then P becomes unitary. So is unitary. Yeah, and if you conjugate by P A, then you will get 1 and 3. Okay, 3 comma, actually you'll get 3. The way I have written it will be 3. So P star A P is going to be, because the first, the eigenvector for 3 has come before, yeah, so it will be 3, 1, 0. Okay, so this is what you'll get. So what happens if A, so see, this is when in this case the eigenvectors eigenvalues were distinct, yeah. But what happens if A has repeated eigenvalues?
You will still get an eigenbasis, right? With of like orthonormal vectors, so you will still be able to do it.
Yeah, so I mean, the theorem says that it's still diagonalizable, right? So if you have a 2 by 2 matrix with orthogonal with repeated eigenvalues, then A is going to be P star lambda I. So maybe I'll write it this way, lambda lambda. So 2 by 2, so lambda lambda P. Yeah. And what is this? This is just lambda I. Yeah, because the middle guy is lambda I. So you can just pull it out. Yeah. And P star P is identity. So what it tells you is that a 2 by 2 Hermitian matrix with repeated eigenvalues is basically a scalar matrix. Yeah. There is no other way. Okay. For 3 by 3, of course, you can have 2 repeated and 1 not repeated. So they are more complicated thing. But if all of them is again the same eigenvalue, then you can argue the same way that there is such a matrix has to be a scalar matrix. Okay. So that's another consequence of this result. That a Hermitian matrix with repeated eigenvalues, 2 by 2 Hermitian is a scalar matrix. Yeah, is that okay?
Yes.
Okay, so let's now look at, so we proved this spectral theorem for Hermitian operator. This is true for more general operator, for unitary operator as well, or more generally what is called a normal operator. Yeah, normal operator on a Hermitian space. So let's discuss what is normal operator. So a linear operator T on a Hermitian space is called normal if it's adjoint, if the adjoint of T commutes with T. Yeah. So this is called a normal operator if T times T star is same as T star times T. Yeah. So they commute with each other. So again, like in the first result here, we have a definition. We have a characterization in terms of how it behaves with respect to inner product. You can have a similar statement for normal operator. So this proposition T is normal if and only if TV TW is T star V T star W for all V and W in V. Yeah. So again, the proof is maybe straightforward. Proof is so what is the proof? So yeah. So T star T star yeah. So let's just T is normal implies T stars same as T star T So that tells you that TV, this is equivalent to saying that, yeah, so now we want to prove that TVT, yeah, so TV TW, this inner product, this thing is same as by definition of adjoint T star TW, yeah. So here I'm not using anything, but we know that T star T is same as T star, yeah. So we can write it as V T T star W, yeah. But what is T? So we also know that T is same as T double star, yeah. So and then this is, then you can say that this is T T star V T star W. Okay. Because if you move T star V this side, then it becomes double star, which is same as T, which is this thing. Yeah. Is that okay?
Yes.
So this is for all beta. Similarly, the other direction is also okay. Yeah. So yeah. So EV TW equals T star V T star W for all VW in V implies V T star TW, and this you move to the other side. So this is V T double star T star W for all VW in V, which is equal to V T star W for all VW in V. And then from here, like we deduced in the previous cases, this implies that T star T is same as T star. Yeah, because you just take the difference. Yeah, and since this difference is 0 for all V in V, then that tells you that T star T W is same as T star W for all W in W. Okay. Is that okay? Yeah.
Yes. Yes.
So again, the normal operator has this similar kind of property. And then there is a spectral theorem for, so before going to, so note that T is Hermitian or unitary, then T is normal. Yeah. So I need not have proved the spectral theorem for Hermitian operator, but it was a short proof. So I said, okay. So if I prove the spectral theorem for normal operator, then for Hermitian operator it follows. Yeah. Because I mean T star is same as T for Hermitian operator, so of course it commutes with itself. And for unitary operator, T star times T is identity. So of course T star is its inverse, and it doesn't matter which order you do the multiplication. So both Hermitian and unitary operators are normal, but normal operator is more general. Yeah, you just want a matrix whose adjoint commutes with itself. So it's much more general. Yeah. So what is the spectral theorem for normal operator? The statement is same. Yeah. So theorem for normal operators. So let T be a normal operator on what happens. You can't see the screen, I suppose, yeah?
No, sir. Visible now.
Okay. Maybe I should have restarted my laptop before. How about now? It's okay?
Yes, sir.
Yeah, so let T be a normal operator on a Hermitian space on a space space V, then V has a basis consisting of V has a orthonormal basis. V has a orthonormal basis. Orthonormal basis consisting eigenvector set. Okay, so this is what, so it's the same statement. And the proof is also somewhat similar. So again, we will prove via dimension. So dimension V equals 1 is okay. Yeah. So we assume dimension is greater than equal to 2. And so let V be an eigenvector vector of T with eigenvalue lambda. Now again, we will look at the orthogonal space and try to prove. And so it's just not that W. Yeah, tell me.
So you also take V to be 0, right?
Say that again.
We also have to take V to be unit length, right?
Yeah. So and let's call it V1. Yeah. So V1 be an eigenvector with eigenvalue lambda and of length 1. Yeah. Such that V1 is 1. Yeah. So it's a unit eigenvector. Yeah. And then W is V1 per. Yeah. Then again V is V1 direct sum W. Yeah. So again, we'll have to prove some things. So again, of course, W is a Hermitian space. That is okay, but we'll have to prove that T W is. So again, claim is that T W is contained in W. And so once we prove this, then we are done. Yeah. So here we will use the fact that T is a normal operator. So so V1 is an eigenvector of T. Okay, so we want to know how T star works on V1. Yeah. So let's look at T star V1. Yeah. So what will be T star V1? So I want to say that V1 is also an eigenvector of T star. Yeah. So so what do we know? So okay, so let's first write down what do we know. Yeah. So we know that TV1 is lambda times V1. Okay. And if I apply T star to it, T star V1, then okay, so let's do it in with what we know. Yeah. So T star TV1 is lambda times T star V1. Yeah. But T star TV1 is also T star T star V1. Yeah. Also T star V1. Yeah. So yeah. Yeah. So I think it will work out. Yeah. So 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 to what can we say about P star V1?
And V1 will also be a lambda eigenvector.
Say that again.
A star V1 will also be a lambda eigenvector, right?
Yeah, but I want to say V1 is a T star eigenvalue vector. Yeah. So this is not what I want. Yeah, so maybe let's try to, yeah, so one should use this pairing somehow. Yeah, so let's try to use the pairing. Okay, so TV1 comma lambda V1 comma V1 is what is just lambda bar is just lambda bar, yeah, lambda bar V1 V1, yeah, which is lambda bar, and what is but this is same as V1 comma T star V1, yeah, right. So um, yeah, so this so that tells you that yeah, so maybe let's not write it this way. So this implies this is V1 comma lambda bar V1, yeah. So yeah, so this is where so this from here I want to, yeah, so this implies if you take the difference V1 comma T star V1 minus lambda V1 is 0, yeah. So Lambda bar V1, not lambda V. Yeah. So I want to claim that this is so T star V1 minus lambda bar V1 is so this is this belongs to W per. Yeah. Sorry, it belongs to V1 per. Yeah, because it's orthogonal to V1. Yeah. So I want to claim it is zero, but so it of course belongs to V1 per, but it's also, I want to argue that it's also a multiple of V1. Yeah. So why is that? It's also in V1.
But as said earlier, we can say that T star V1 is lambda V1.
T star V1 is T star V1 is what? Yeah, so anyway, so what we can do is we can write T star V1 as something, so it's some multiple of V1 plus something in the orthogonal component, but so something is missing. So it is it is an eigenvalue, a vector with eigenvalue lambda bar is what I want to say. Yeah. I mean, there's not much trickery involved. It's just this. So let's try to see. We haven't used the hypothesis so far. Yeah. So yeah. So T star V1 is T star. So, so T star V1. So of course this lambda V1 is in V1. If I show that T star V1 is orthogonal to W, then it has to be in V1. Yeah, it has to be a span of V1. Yeah, so note that T star V1, comma W is same as V1 comma TW. Yeah, but why is TW? So we want to show that TW is in going in circles. So see what did I miss? But there was no trick in this. I see. Yeah. Okay. So yeah. So maybe yeah. So what we do is we write T star V1. So we can write it as uh, V comma. So we try to do this orthogonal decomposition. I mean, we write it as a projection onto V1. So for that, what you do is V comma T star V1. V1 comma T star V1 over times V1 plus T star. So I don't know. So this is not V1 comma. So this how will this help? V1. Yeah. So I'm just rewriting this. Yeah. T star V1 as adding this and subtracting this. I'm doing nothing in sense. Yeah. Now, but this vector is orthogonal to, yeah, so this is orthogonal to this, that we know. Now, this I have already seen, so I don't, so yeah, so okay, yeah, so the maybe the one should prove it directly. Yeah. So okay, what do we want? We want to show that T star V1 is lambda V1, lambda bar V1, right? That is what we want to show. So let's just try to show it directly. Yeah. So T star V1 minus lambda bar V1, we want to show is 0. Yeah. So in the inner product space, best way to show something is 0 is just take the inner product with itself and compute that it is 0. Yeah. So let's try to compute this minus lambda bar V1. Yeah. And this is where we can use the fact that it's normal. So so actually, if T star is normal and this lambda lambda bar minus so this is basically what is this? This is, I mean, one can expand it, but I'll do some shortcut. Lambda bar I V1 comma T star minus lambda bar I V1. Yeah. So this is same as this. Yeah. But T is normal, and hence T star is normal, and identity is also normal. Yeah. Identity commutes with everything. Yeah. So lambda bar identity is also normal. Yeah. So and difference of two normal operator is again going to T star minus lambda bar I is also normal. So if A commutes with A conjugate and B then A plus B will and T star and I commute. Yeah. So T star I times T star I is same as I T star. Yeah. So what I'm trying to say is that T star minus I lambda bar I is also normal. Yeah. So is normal. Or T minus lambda I bar, T minus lambda bar I is normal operator. Yeah, because T is normal operator. So you just do the conjugate and multiply in. So T star. So is this okay? Yeah, that this is a normal because T star T minus lambda I star is basically T star minus or let's put it lambda I. Yeah. So is basically T star minus lambda bar I, because I adjoint is I. Any questions? So this adjoint of this is this, and of course E minus lambda I times T star minus lambda bar I. This of course is same as T star minus lambda bar I times P minus lambda. Yeah, because if you multiply it, expand it through, right? So you will get T star, lambda T star, lambda bar T, and plus lambda bar, and same terms you'll get here as well. Yeah. So T minus lambda I is a normal operator. So this inner product is same as since this happens, this inner product is same as T minus lambda I V1 comma T minus lambda I V1. Yeah. That is the theorem, that's the corollary which we proved here. Yeah. So actually you don't, if you expand it, you don't need all this. Yeah. TW is same as T star V T star W. But of course you can expand it and do it as well. So you don't have to apply any result. So from here I could have just expanded and still got the result. And then this becomes, but what is this vector? So V1 is a lambda eigenvector. Yeah. So TV1 is same as lambda I V1. Yeah. So this is 0, right? So what you get is that, so this implies hence T star V1 is lambda bar V1. Yeah. So T star is also so V1 is also an eigenvector for T star. Yeah. So now it is easy to show that W is closed under the action of T star. Yeah. So so now we will show. So now let W be in W, then what do we know? We know that W comma V1 is 0. Yeah. And we want to show that, so let's see TW. Yeah. So we want to show that TW comma V1 is also 0. So TW comma V1, the inner product, is same as W comma T star V1. Yeah. But now since we have proved that T star V1 is just lambda bar V1, this is W comma lambda bar V1, which is lambda bar W comma V1, which is 0. Yeah. So this tells you that TW belongs to. Okay. And then the rest of the proof is same. Yeah. Now use induction. Use induction hypothesis to get that get V2 to Vn an orthonormal basis of W consisting of eigenvectors of T restricted to W. Yeah. So T restricted to W is again a normal operator. So to check normal operator, again you have to do element wise check. Yeah. So maybe one should write here T restricted to W is a normal operator on W of and dimension W is n minus 1, where n is the dimension of B. Yeah. So okay, so V1 to Vn is and is the required basis. So of course, V1 to Vn is also normal, and it's consists of eigenvectors of T. Okay. Is that fine? Yeah. So this is where we use the normality to prove that T star V1 is same as lambda bar V1. Yeah. So basically the inner product is going to be zero. Okay. Any questions or comments? So again, there is similar consequence for matrices. So the A be a n cross n matrix such that A star A equals A star, then is diagonalizable, or then let's just write it in a more reasonable way. And there exists P unitary matrix such that P star AP is diagonal. Okay. So this is the spectral theorem. So there are many consequences of spectral theorem which I want to state, and there are also some. So I took a shortcut to spectral theorem. So I skipped a few propositions and so on, which are proved in R10 to get here. So I'll state and prove some of them maybe in the next class. So, but maybe so there is a spectral theorem even for, so this is for finite dimensional vector space. So there is a spectral theorem for Hilbert space or more infinite dimensional, which you'll see maybe in your functional analysis course. So some of the results, so there are normal operators. So there is a operator, then you define its adjoint and normal operator and so on. So